We have Clifton from Einstein University, so we'll be talking on nonlinear structures, nonlinear structures.
Thank you very much. So it's a pleasure to be back here again. So I was at the first meeting 6 years ago when I spoke about a similar subject, so cosmology with discrete structures in it. At that time I was talking about the approximate model created by Clifton in the 50s. We should be looking at the optical properties of it at the time. So this talk, quite nice to be able to come back and talk about a similar subject, but talk about the development of the models this time that we use to model nonlinear structure in the universe. So the interest with the model is approximate, and now we have much more sophisticated models with some exact properties, some perturbative models, and there are numerical approaches as well that we use to study spacetimes that have regular arrays of discrete particles in it. So a little bit of this overlaps with the talk I gave for George's birthday last year, so if anyone was here, apologies for that, but stay tuned, there's new things in here as well. So the particular way that we're going to go beyond concordance in this is to talk about nonlinear structure, by which I mean structures that have nonlinear density contrasts. So the reason for that, of course, is that the universe has nonlinear density contrasts in it. So this is the famous picture by Hubble, the deep field. And the real universe has, at least in the visible parts of the matter, has very large energy densities with very close vacuum in between them. There's dark matter halos around these things, of course, so this might be slightly misleading, but even the dark matter halos should be expected to be highly nonlinear on small scales. As well as a complicated distribution of matter that you can see here, we've also got a nonlinear theory of gravity. So the current favourite theory that concordance model is based on is Einstein's theory, of course, and all of the generalizations as well, that I'm aware of at least, contain nonlinear physics in the field equations. So we've got complicated matter distributions, complicated gravitational theory, and we have no fixed background geometry in which to use. So the idea of background geometry, in fact, if you're using that kind of language, implies that you're using a perturbative approach to gravity. The real universe has no fixed background because there can be no fixed background in general relativity. There's also no symmetry in the real universe. So although it might look like there's symmetry up to smoothing on very large scales, the space-time in between each of these objects has no symmetry, no killing vectors in the real universe. And the real universe is not algebraically special. So you can compare this complexity, energy density, gravity, no fixed background geometry, no symmetry or special properties of the space-time to the model that we use to interpret all data. So the standard approach to cosmology, the concordance model, starts off by hypothesizing an FLW background. So I've written hypothesize here on purpose. So I'm going to talk a little bit on the next slide about what's required, in fact, in order to show that the universe is close to FLW. The next step is to add linear perturbations on the large scales, which describe small density contrasts when the fluctuations have very large wavelength. On small scales, the current state of the art is still to treat gravity as Newtonian, and then, at least for all of the current applications, higher order effects from gravitational fields are neglected. So there's been a lot of work on this recently, of course, in preparation for SKA and Euclid and LSST and so forth, especially by people here in Cape Town. But I wouldn't say that this is currently part of the concordance model, it's kind of an extra part of this point. Okay, so the question is then, can we use this extremely simple model of the universe to interpret all aspects of an extremely complicated universe? And is there anything we might miss, or is there any way of proving things that we're hypothesizing when we apply this model? So theoretical challenges that I see, at least in applying this kind of model, are associated with the existence of a background and the way that we treat first-order perturbations. These become especially important if we want to start considering high-order effects in gravity. So the first question we might ask is the observer's FLRW model an emergent paradigm, or is it supposed to be close to the actual geometry of space-time? So these are two quite different things. If it's the former, if we have a very complicated universe which is described on average with a Friedmann universe, then how do observational constraints relate to fundamental physics? So if we're constructing a Hubble diagram fitting a Friedmann universe to that, if the Friedmann universe is only an emergent paradigm, then how do we infer things about the equation of state of dark energy from that kind of situation? So this is what's often called back reaction in the cosmology literature, which is popularized recently by Thomas Buchard. It's equations that have this Q that quantify what the effect of back reaction is and how you would link the average expansion to the microphysics that exists in the universe. So the back reaction problem has various other problems that are associated with it in order to try and make definite statements. So there's a fitting problem, which George and Bill Stoker wrote about a long time ago, which is how you would try and fit an emergent FLRW universe to data. So there's not a unique process for doing this, and you could end up with different types of FLRW models that describe different things that are associated with physics. So there's quite a lot of problems involved that need to be solved here, and I would say at the moment there's no unique way even to average tensors in a space-time. So there's many proposals on how to do this. There's a unique definition of how to do it, and there might be different ways, might be better ways of doing it for different situations. So how to apply these and how to understand the effects of back reaction, how to do fitting and how to do averaging are still largely open questions in cosmology. So if we want to use the FLRW model as an emerging paradigm, then we really need to understand these. We need to quantify them and bring them to precision cosmology. If it's the latter of these two options, if the real universe really is close to the actual, if the FLRW model is close to the actual geometry of space-time, then how do we prove this? So you can hypothesize it and show that it's consistent with observations, any given set of observations perhaps. But how would you prove from observations that we live in a universe that's close to FLRW, which is what we really want to do? So there's been a lot of work on this over the decades as well, of course, starting probably with Ellis, Garrett, and Sachs. It's one of the most significant steps, which was generalized by Roy and George. The idea here is that if the observer sees CMB that's close to isotropic, then that implies that the geometry of space is close to homogeneous and isotropic. It's not quite as simple as that. It's not just the CMB that one observer measures, it's the CMB that all observers in the entire universe at all points in time measure have to be close to homogeneous and isotropic. And you also have to assume the gradients of multiples of the CMB vary slowly from place to place. So that's an awful lot of information which is in principle unobservable. If you want to go away from the CMB and you want to see what observables are required to say you live in a Friedmann universe, if you do, then the full data set is really formidable. So you need galaxy number counts, luminosity distances, peculiar velocities on the sky, and the lensing on the sky at all points on the sky and at all redshifts, if you want to make this kind of statement. As yet, as far as I'm aware, there's no generalization of this to an almost theorem, where you have an almost Friedmann universe. And it's not clear how imperfections in data, gaps in the data between different observations would affect that kind of statement. So this is really for the far future, this kind of test. It's in principle possible, even with SK at Euclid. This is not going to be a feasible challenge. So that's the background. What about perturbation theory? Is it sufficient to model all structures using perturbation theory? And what could go wrong? Well, if we're using cosmological perturbation theory, then a strict application of this theory requires that the density contrasts will much less than 1. So this is expected to be fine on large scales, and it looks fine in the CMB. While on small scales, of course, this isn't valid. Density contrasts are much larger than 1 when we get down to scales of 10 megaparsecs or so. And one thing that people often say is that you have to go beyond linear perturbation theory, but that's no good either. You go to high accuracy, but you still have to have this condition valid if you want to use cosmological perturbation theory at all. A second potential problem is that the curvature contributions from nonlinear structure dwarf those of the cosmological background. So if you work out the Ricci curvature scalar of the geometry of space in this room, it's many orders of magnitude greater than the Ricci curvature scalar associated with cosmology. So this is kind of problematic if you're doing a top-down approach to cosmology. If you're hypothesizing that FLIW background and then putting things on top of it, the things you put on top are much, much larger when it comes to solving the field equations. No sensible person would try and solve the geometry of space-time in this room by taking into account the expansion of all the space. But what we have to do is subtract off this enormous contribution, and then what's left we solve for in order to find the expansion of space from the Friedmann equations. So that's potentially problematic if you're using a top-down approach. What would be much more satisfactory would be a bottom-up approach, where we have the structures in the universe, we work out what the emergent expansion would be. A third possibility is that non-perturbative or higher-order gravitational effects can play a role in the formation of structure. So this is a possibility that you can't investigate, of course, if you're only using linear gravity. I'll try and convince you that there's reasons to think that these things might be important. So to answer all of these questions, we need new models. Trying to understand the back reaction problem and this very challenging task of trying to prove that the universe is close to FLIW, close to impossible, or perhaps even impossible in the back reaction problem, unless you know what the geometry of space-time is. That's because the equations that describe these things aren't closed systems. So if you want to try and use them without space-time, you have to make assumptions about how different quantities involved are behaving. If we have models of how FLIW behavior emerges from inhomogeneous spacetimes, then we can make more definite statements. And if we can consider more and more general models, then we can say more and more general statements about when we expect an FLIW model to be valid, and what the possible deviations could be of the expected behavior. Okay. So there's 3 different ways. This is a very general kind of splitting of how you might construct a model of spacetime, of course. So I want to talk about some exact methods that you can use to investigate some of the properties of an inhomogeneous spacetime. I'll mention only very briefly some numerical approaches. Eloise Ventuelia is going to tell you more about that. She's the real expert, so I'll leave the details of that for her. And some perturbative methods that we've been developing as well. So I don't mean cosmological perturbation theory here, I mean new types of perturbative expansions that can be used to construct cosmological models with non-linear density contrasts. So these exact approaches I've been doing with these collaborators, perturbative approaches with these ones, and these are some of the authors of the very important numerical work that's been done as well. So let's start with the exact approach. So there's a very large literature, of course, on exact cosmological models. It goes back decades, and many researchers have spent their careers looking for cosmological solutions of Einstein's equations that describe universes that have nonlinear density contrasts. There's a compendium by Andrzej Krasinski, which is an excellent overview of the different types of model that are constructed. These are usually constructed by assuming something like global symmetries from the outset, or some kind of algebraically special property which allows you to integrate Einstein's equations. This is a perfectly legitimate way to proceed, of course, and gives you a lot of information about how inhomogeneous cosmologies can behave, but isn't necessarily exactly what we want in order to answer these problems. So the exact models, or the exact properties of models that I'm going to try and describe to you are the types of universes that this picture is intended to illustrate. So where we have large inhomogeneous density contrasts that are regularly arranged, but where you have no local symmetry at all. Okay, so if you consider closed cosmological models filled with uncharged, non-rotating black holes, then that's about the simplest thing that we can start with. It turns out that if we consider that type of universe, then there are some exact statements that we can make about what the emergent cosmological properties would be from black holes that are arranged in that type of universe. So I'm not talking about Swiss cheese models here, where you start off with a Friedmann ansatz for large-scale behavior, excise a region and put in Schwarzschild geometry. And if you do that, then you get some interesting properties, interesting questions about how the geometry of the Schwarzschild solution affects the lensing of light and so forth. But the large-scale properties of a Swiss cheese model are always dictated by the Friedmann solution that you put those black holes into. What I'm talking about here is a universe that only has black holes, but there's no pre-specified large-scale cosmology, where the large-scale properties of the space-time emerge after you solve for the multi-black hole solution. So it turns out that the exact geometry of a space of this type can be found at the maximum of expansion. And this is using the method of geometric statics that Charlie Visner, Richard Lindquist, and other people developed in the 50s and onwards. It's used a lot in black hole physics for the initial data, because you can solve using geometric statics the exact geometry of the initial data, which you can then evolve numerically into more complicated situations. This can be applied to cosmology. And if we apply it to cosmology, then these are the types of geometry that we should expect to see. So on the left here, this is what the maximum expansion would be like if you took a one black hole universe. So you know exactly what the geometry in that case is. This is the Schwarzschild geometry. And if we take a time-symmetric slice through the Schwarzschild geometry, we end up with what's called Flamm's paraboloid, which when you dimensionally reduce it and embed it in flat space, has a geometry that looks like this. So we've got two asymptotically flat regions, one at the top here and one at the bottom. An observer who's sitting in either of these would think that we're seeing one black hole in the center here. And the horizon in this space-time is the smallest topological sphere that can fit inside this three. It's like the Einstein-Rosen ridge. In the case of Schwarzschild, we know that this is an event horizon. If you've only got the local geometry, we can't tell where an event horizon is. The best we can do is the apparent horizon. And the apparent horizon in a time-symmetric geometry is always the minimal sphere that you can fit inside a third. So this is what one black hole looks like. If you consider a universe that has many black holes in it, then the embedding diagram should be expected to look something like this. So this is a cartoon of an embedding diagram, by the way, not the actual embedding diagram. That probably can't be embedded in two-dimensional space. But the idea now is that we've got a cosmological region in the middle here, a bulbous space, which looks like it's got close to constant intrinsic geometry when you get far away from all of the black holes. We have a number of these throats coming off the cosmological region. These black bands indicate where the minimal sphere that you can fit inside that throat would be, which therefore correspond to the apparent horizons of the black holes. On the far side of each of these throats, we have an asymptotically flat space. So I've indicated two of those in this diagram. You should expect them to similar spaces to be plugged onto the end of these. So each of these is similar, though not identical, to one half of Flamm's paraboloid. And these are the types of cosmologies that you can construct using geometric statics. So in principle, we can construct any configuration of black holes on a closed space. There's no limitation as to how we distribute these things. But for the purposes of studying the emergent cosmology, it's useful to try and place the black holes in a regular way as possible, so that we get something that looks most of all like a Friedmann universe when we consider it on the large. So if you want to consider black holes that are equally spaced from each other, there's only 6 possible ways of distributing them on a 3 sphere.
In which sense regular?
So that the nearest neighbours to each black hole are equidistant, and that distance is the same independent of which black hole you choose. So it's like a lattice of points on a 3 sphere. So these cases have 5, 8, 16, 24, 120, and 600 black holes, and they're the only ones that you're allowed if you insist on that criterion. Okay. So the locus of points that are closest to each black hole is a regular polyhedron, and I'll call that a cell of this putative lattice. And the faces of each of these cells is reflection symmetric. So reflection symmetry simplifies the geometry of the space each of those points. So we've got vacuum spacetimes here, so the 20 independent components of the reaching Wagner curvature get halved immediately because we know all of the reaching components vanish. And if we consider the geometry of space on reflection symmetric surfaces, those 2-dimensional spaces, you know half of the Wagner curvature as well, so we reduce immediately to 1/4 of the data you would have in general. And because each cell face of these polyhedral cells are symmetric when the planes meet, at the edges of the cells we have even more symmetry. In fact, we only have 2 independent components of the geometry left at those points. So we come close to knowing everything about the geometry of space at the edges of these cells, which are the points that are furthest away from each of the black holes in this diagram, which for example, we're trying to get to here. So the idea is to construct a universe of this type. This is Charlie Chaplin in a hall of mirrors. So if you the mass for every Chaplin, and you consider each of these cells inside mirrors to be the types of polyhedra that I've been considering here, and you have a universe full of Charlie Chaplins, you can solve Einstein's equations for to find out how they expand. And more geometrically, a dimensionally reduced version of this would be embedding polyhedra inside spheres, seeing where the points of the polyhedra touch the sphere and then joining them with lines. If you did that, the structures inside would be the types of cells I'm talking about. And you can then see why there's 6 regular arrangements of black holes, because there's 6 regular convex polyhedra in dimensions. So So these are the 6 lattices that I want to talk about. And if you solve for the geometry of space as a maximum expansion, then you get scale factors that look like this. So again, this is a dimensional reduced version, so I can illustrate it practically. The idea, what we've done here is taken a slice through 3-dimensional space. These are exact solutions to Einstein's straight equations. And the distance from the origin of each of these 3D plots indicates what the size of the scale factor is. So this is the 5-mass universe, 8, 16, 24, 120, and 600. And you'll notice there's only 4 tubes here. So this is only one slice through the 5-dimensional space that has all 5 of those black holes in it.
So you have clusters of black holes?
No, they're not clustered actually. So they look like they're clustered here, but that's only because I've taken a slice. They're actually perfectly regularly distributed. So the black holes in these diagrams are the positions where the scale factor becomes large, and these tubes actually go off to infinity. And the infinitely large scale factors at the far end of these tubes means that the geometry of space, when you get close to the point where you place the black hole, is isometric to a flat space, which is why you come out towards these flange regions here. So these are all black holes where there's a tube. So as the number of masses is increased, so as you go from 5 to 600, the geometry of the cosmological region, you can perhaps try and see just by eye there, looks a bit more like it's spherical as you get down to this kind of stage. In fact, it's not exactly spherical, but you can make statements about the approach to spherical geometry if you put in arbitrarily many masses. There's an excellent paper by Relativistically on that subject. The geometry of these spaces is actually Riemann flat at the asymptotic region of the tube, so when you go infinitely far away, and at the points that are equidistant from all of the masses. So if you imagine taking a mass point that's as far away as possible from each of the tubes, then the geometry of that point is Riemann flat. So the scale of the cosmological region approaches that of a dust-dominated FLRW solution as a total number of masses in the universe becomes large. Because we've got exact geometries now, we can quantify this exactly. So what I've got here is a ratio of scale factors. You probably might be able to read this, it's a bit blurry. So there's a scale factor for these discrete cosmologies, which you can measure in different ways. It's not a unique definition of scale for these quasi-spherical regions. But I've got 2 different measures here that I took the blue and red curves, which will not, although not exactly the same. So you can see have a similar trend. And the ratio of the scale factors from the discrete model and the Friedmann model that has the same total mass in dust is given by the y-axis here. So if it were 1, we'd have exactly the same scale as the Friedmann universe that we're trying to model with the same total mass in dust. And as the number of masses becomes large, so as we move to the right on the x-axis here, the log base 10 of the number of masses becomes large. When we get down to 600 masses here, we get very close to the Friedmann value. If we have a universe that's extremely inhomogeneous and very unrealistic, of course, in that case, with 5 or 8 masses, we've got order 10% changes in scale. So the difference between the scale of homogeneity and inhomogeneous spaces is about 1% by the time the number of masses gets up to the order of about 1,000 or so. And you can see also that these results match the approximate results that were found by Lindquist and Wheeler to quite good accuracy. So the Lindquist-Wheeler results are the dotted line here. So that's the approximate models that were constructed by Wheeler and Lindquist in the 1950s. And it's quite ad hoc in a way. It's like a big-in-a-slice type approximation for gravity, where you treat the geometry of space as being specified by the mass that you're closest to. So it's not an exact solution of Einstein's equations, but they were able to get an estimate for what they thought the scale of such a space should be. And it's very close to the exact results, in fact, or relatively close. So the spaces I've shown you there are exact solutions, and they're vacuum solutions, and they cover an infinite domain. So from existence and uniqueness theorem, you know that at least locally there's a unique evolution of those spaces. And if we apply numerical relativity techniques, then we can evolve that initial data forward in time to find full space-time. So this is work that Elisa and other people have been doing. So I'll just show you a slide from their work from 2012, work with Clifton, where they started off with exactly the same initial data that we had on the previous slide there, but the 8 black hole universe. And at t equals 0, which is this point here, they've rescaled the 2 models so that they have exactly the same size but now contain different amounts of mass. So the FLRW model is the dotted line here. So that's an exact solution, of course, of dust field spatially closed FLRW model, which if you start out at this point, you know exactly how it's going to evolve into the future if you plot time in units of the mass in the dust field. The hollow circles here are what they found numerically when they evolved this initial data forward, and they found that the dotted line was very close to the hollow circles, at least until the errors started to become larger with numerical data. So these methods are an excellent way of getting the full geometry of space-time, of course. If you start with exact initial data, you can evolve away from that data to find the geometry of the full space.
So maybe I missed it. So there is a departure between the numerical behavior and the FLRW. Yes. So where does it come from? Is it maybe actually that's
we actually made the mistake of not putting error bars in this plot.
So
some error bars that would be much bigger. There's a way to reduce the error bars, make more accurate simulations, and if that happens, the tutors get put in again.
So that's what the numerical work told you, or told in 2012, I believe they've been working at it since then. You can use other methods as well to try and evolve space. So with Shel Roskist and Daniele Gregoris and Reza Tavakol, we use the electric part of the Weil tensor to get the leading contribution to the evolution of the curves that are the edges of these lattice cells we're talking about. So remember, those highly symmetric curves have enough symmetry to reduce the independent degrees of freedom in the Riemann curvature down to 2. And the electric part of the Weil tensor is one of those, the other one vanishes in the initial data. So the electric part of the Weil tensor is the one that contains the Newtonian unit of gravity, so you'd expect this to contain like attractive force between the black holes. So if you take this contribution to the evolution of the edge of a curve and you integrate it, you can do this, make quite a lot of progress analytically in fact. And these 6 lines, there's a yellow and green one almost coincident, but there are 6 lines on this curve as well as the dashed Friedmann curve. The positions of them at t equals 0 here are the positions that I showed you on the previous plot, where we have something like 20 or 30% deviations from the expected Friedmann values. And as we evolve the space forward, it starts to collapse, and initially it looks very much like a Friedmann curve, and then starts to deviate from the Friedmann behavior and flattens out in fact. So what's happening here is each infinitesimal region of the space is decreasing at the rate that's expected from a dust-filled FLRW universe. But the evolution of the global scale is different. And that's because the effective mass that you would get if you considered the local version of the Friedmann equation at each point on the edge of each of these cells has exactly the same form as the Friedmann equations for a dust-filled spatially closed cosmology, but with a different mass at each point, because they're local equations now rather than global. So initially, the behavior looks close to Friedmann, and then what happens is that some of the curves start going closer and closer toward the end state of their collapse. They don't form singularities, but the behavior does start to deviate from the Friedmann behavior. So this is something like Thomas Buchard's back reaction scheme, I think, where you have different types of expansion at different points in space. And the average, or integrated expansion, can deviate from what you'd expect from a Friedmann universe. So, remember I told you there were 2 independent degrees of freedom in the Riemann curvature. So the first one that's non-zero in the initial data is the electric part of the Weil tensor, which causes the collapse that I showed you there. The second part is the second independent part of the Weil curvature, and therefore the Riemann curvature is the magnetic part of the Weil tensor. This one? Okay. So this is initially 0 at the maximum of expansion. So that would be called in the mathematical cosmology literature a silent universe. It does evolve away from 0 and eventually contributes to the full evolution. So Eloise and her collaborators published work on this first, although we were working at the same time, they beat us to it. They found that this is non-zero in the future evolution of that initial data. And the contribution can rise to about 1% before the numerical and perturbative approximations start to break down. So what I've shown you in this plot is the effect that the magnetic part of the Weil tensor has on the large scale, the scale of the cosmological region as a fraction of what it would be without that contribution. So the different curves here again correspond to the 6 different models. So this is the 5 black hole universe, 8 black holes, 16, 24, with 120 and 600 hidden down here. So the way that we constructed these curves was using Taylor series expansions away from the visual data. And we considered the first 2 non-zero terms, which come in a relatively high order in that kind of expansion, showing, I think, that there would be high order perturbative approximations as well. So these are relativistic effects causing a change in the large scale properties of the universe. And the solid lines here end when those 2 contributions to the Taylor series expansion become the same order of magnitude. So at that point that the series expansion breaks down, we can no longer use that reliably. So the end of the solid line is where that happens at one point on the edge of the curve, and then the dashed line is where it happens at every point. So for the 5 mass universe, we can evolve the whole thing before this perturbative approach breaks down, and we get to something that's approximately 0.5% of the contribution to the full scale of the universe. So that's a relatively small contribution, but the contribution actually rises as the number of black holes becomes bigger. So for the 8 mass black hole, you get to around 2% correction before the series expansion breaks down. And if you look at the yellow and green curves down here, are getting larger values at earlier times, although the expansion breaks down at earlier times as well. So this constitutes a contribution to the large-scale expansion from integrated higher order parts of the gravitational field. And this seems to me to be reminiscent of the gravitational wave memory effect that Christodoulou found, using his non-perturbative approach to gravity that he developed in China. So in that approach, if you have an inspiraling 2-body problem, you have gravitational waves being emitted, and the leading order part of that is an oscillating quadrupole. So you have this well-known picture of the circle being deformed into an ellipse and oscillating backwards and forwards. What Christodoulou found is that higher order effects in the gravitational field mean that after the wave train has passed, the circle doesn't return to a circle, it stays permanently deformed, although the geometry of space returns to Minkowski space. And that comes from, if you're using a perturbative approach, Kip Thorne showed that comes from integrating the second order parts of the gravitational field. It's effectively the gravitational field of the gravitational waves that were previously emitted. And it's an excellent example of non-perturbative gravitational effects having a large effect, a large end effect on a physical system. It seems to me this is somewhat similar. We've got high order parts of the gravitational field, which are being integrated over cosmological time, and are becoming comparable to the size of the leading order contribution, which comes from the electric part of the Wahl tensor, which is contained in that Newtonian Coulomb part of the gravitational field. So, this is kind of just a very brief introduction to a very large amount of work that's been done by a large group of people. So perhaps I can give you just a few references for extensions and generalizations of this kind of model. So there's a lot of numerical work being performed by Schulman Yu and Eloise and collaborators. And they've considered spatially flat cosmologies. So in that case, you can't solve the initial data exactly, but you can do it numerically, and you can evolve it numerically. And they find in one of these studies, I believe, that the evolution remains close to a frequent universe if you use that approach until the numerical error becomes large. Last one here is a work in process I'm doing with Bernard Carr and Alan Coley, where we use other measures to try and construct spatially flat initial data for an infinite universe. The models I showed you didn't have any lambda in them, didn't have any matter fields of any type in them. In fact, you can include lambda in these models in a relatively straightforward extension of them. This was done numerically by Schulman Yu, and recently Jesse Dirk and I did this exactly. It was a case of a spatially closed cosmology. In that case, the initial data is no longer time symmetric. It's no longer an actual surface of the foliation of the space-time. But it is a constant mean curvature slice of the space-time. What you find in fact is that if you plot the same graphs that I showed you before, the existence of lambda has absolutely precisely zero effect on the change of scale. And the final thing I've got here is models of exponential fields. So these are 2 works in progress with Rashid Habibi and Jesse Dirk. We've been working on including electric charge, so solving the Einstein-Maxwell system instead of Einstein's vacuum equations. And the last one with Bernard Carr and Cody is using a scalar field. So solving for black holes that have scalar hair and get interesting and novel behavior if you allow that possibility. So they should be interesting. Okay, so that's the kind of work that's been done over the last 6 years, since the last one of these meetings, on trying to construct new types of models of this type. So the exact solutions are interesting, I think, and numerical work is very interesting because it allows you to include all of the relativistic effects. So you're not missing out anything at all. But it's not necessarily the most flexible of approaches. In order to get a more flexible approach, it's useful to think about perturbative approximations that capture some of the essential features of those constructions, but allow you to add matter fields and construct things a bit more generally. So the first attempt at doing this was with Biraj-Sangai, and in 2015 we published work on the perturbative approach modelling a space-time around each of these masses using post-Newtonian gravitational theory. So post-Newtonian theory is quite different to cosmological perturbation theory. It doesn't expand the quantities in the same way, and post-Newtonian theory is designed, in fact, to be used in physical systems that have nonlinear density contrasts. So if you want to model each of those cells as containing a cluster of galaxies or some distribution of matter, then post-Newtonian perturbation theory seems like it's the type of perturbative approximation we ought to be trying to use. So the idea here is that, again, we split the universe into different cells. And if we consider a spatially flat universe, then the only way to tessellate a spatially flat universe with regular convex polyhedra is if you use cubes. So we've got 2 cubic cells, an example of how to do this. And you treat the space-time within each of these as being modelled using post-Newtonian theory, then construct a cosmological model by matching together these 2 regions of post-Newtonian space-time using Israel's junction conditions at the boundary. So we want the first and second fundamental forms of that boundary to be the same on either side as we go through. We don't want to set X and Bella, and if we want the union of them to be a solution to Einstein's equations. So although post-Newtonian theory, as it stands in the bulk of the literature, isn't capable of modelling cosmology, because we can't model things on horizon-sized scales, we can model small regions of space and then patch those together in order to get a global cosmology. And if we do that, after about 60 pages of maths and these 3 papers, we get this equation. So this is the evolution of the scale factor, which is the integrated length of one of these cells in this case, because there's no frequent background to this space-time, in the same way there wasn't in the exact solutions. That's what we call the scale factor here. The dot is the proper time of the set of observers who are co-moving with the edge of this boundary, and where the congruence goes inside the bulk of it as well. We find that the square of that, so the Hubble rate, is given by terms that are equal to the integrated mass density inside the cell, plus the integrated density of radiation, where Biraj extended the post-Newtonian formalism so that it can include large amounts of radiation and can include global spatial curvature. That's what these 2 terms are. We've got a cosmological constant term, which looks, again, just as these terms do, like the source terms for the frequent equation, but we've got a series of extra terms here as well, which we call B. So something somewhat analogous to Thomas Buchan's Q, perhaps. So this B is given by this quantity. We've got an equation in this paper which gives this generally for any distribution of mass. Because it's post-Newtonian gravity, you can integrate using Green's functions for any distribution of mass you want. If you take the mass as being located in the center of the cell, then that simplifies the setup, and then you can make quantitative statements about what the size of this back reaction term should be. And what you get is something that decays like 1 over a scale factor to the power of 4 here. That's what this prefactor is telling you essentially. The L here is the length of one of these cell edges. That's the only extra scale that gets introduced into the problem. And we've got these 3 terms. So the first one exists in the absence of any radiation or spatial curvature. And this is a numerical approximation, by the way, not exactly 1.5. But we have this contribution from the inhomogeneity of the matter fields. The existence of radiation in the presence of inhomogeneous matter fields gives you a contribution that looks like this, and spatial curvature like this. Again, lambda makes absolutely no contribution to this, other than numerical factors that are included here, which goes along with the exact result I was just telling you as well, that lambda has 0 effect on back reaction. So these terms, leading order 1, one for the matter fields here decays is 1 over e to the 4. So functionally, in terms of the gravitational effect that has on the large-scale expansion, that looks like a kind of effective radiation component of the universe, which fits in actually with work that that Stephen Green and Bob Moore did, although it's a very different formalism. And well, I think ours is more general. It's the same contribution in fact to the Friedmann equation that you get. Okay, so again, this is a lattice construction. It's a perturbative approach to try and construct something that can be generalized from the exact configurations I was saying before. But if we remove the restriction of reflection symmetry, so we don't have a lattice where every boundary is reflection symmetric, then what we need to do is include a global FLW background from the outset. So in the previous slide, there was no FLW background, the large-scale behavior just emerged from solving the post-Newtonian equations. If we want to have even more general configurations, then we can't assume that kind of emergence. We have to postulate a global FLW background from the beginning. We do get consistency conditions for that FLW background to exist. So the next stage that I'll describe to you in these post-Newtonian expansions is including not only small-scale fluctuations that you can model with post-Newtonian gravity, but large-scale fluctuations as well, which you would model with post-Newtonian theory, with cosmological perturbation theory. So if you want to include both of those things, if you want small-scale fluctuations that can be nonlinear and large-scale fluctuations that are linear, then each one of those is outside of the regime of the other. But you can include both of them at the same time when you're perturbing space-time. And probably that's looks like a two-parameter perturbative expansion of this postulated FLW background. So the idea here is that you've got the real universe, which has both large wavelength and small wavelength fluctuations in it, and this is a perturbation in the post-Newtonian expansion, and then a perturbation in the cosmological sense. So the way we constructed this path from the perfect Friedmann background with Newtonian and cosmological perturbations is the same as cosmological perturbations and then post-Newtonian perturbations. So this kind of commutativity of these different maps between the different types of perturbations is required for this to make any sense at all. And the way that we talk about the tensorial quantities that are required in order to solve the gravitational field equation, so this is the metric and the matter field, which are lower rank tensors, are all expanded in both the cosmological perturbation expansion parameter and the post-Newtonian expansion parameter. So we have two series here running over both the cosmological and post-Newtonian expansions, and if you want this to be a relativistically valid way of describing a universe, we need to understand how gauge transformations work as well. So we need to know that if we make infinitesimal transformations, order transformations in space-time, we're not changing any of the physics. So the gauge transformations are specified using this exponential map, where, what you can see at the left side, is the gauge generator, which acts upon the tensorial quantities that exist in this manifold in this way to give us the same quantities in the new coordinate system. So the gauge generator in this case has to be not only a function of the cosmological term parameters, but also all of the post-Newtonian ones. So this becomes a lot more complicated than it is than the ones you've seen from Barney in cosmological perturbation theory because of those two parameters, and also because it turns out we have to go to second order in order to get estimates for the leading order parts of the gravitational field at large scales. So just to introduce why we need these two different types of expansions, let me try and illustrate it with this kind of conformal diagram. So if you've got the past light cone of some event in space-time x here, and the future light cone of another one, if we're considering cosmology on horizon size scales, then we're considering regions of space that can contain both of these things. And in this case, you can formulate Einstein's equations as a set of null wave equations, which I listed initially, but the people who study conformal generalizability these days have done a much nicer way of that. But the solutions to Einstein's equations are always integrated on null surfaces. And that means that the variations in distance are on an equal footing with variations in time. There's no difference between those two things if we're considering space-time on horizon size scales, and that means that if we've got a cosmological perturbation theory parameter epsilon, we can only have, all we can do is say that we have each of our quantities from the background with a perturbation on top of them. And there's no difference between the sizes of these things a priori in the expansion. in any way. So that's regular cosmological perturbation theory, which I suppose most of you are very familiar with. Post-Newtonian sector is different because we're considering only a small region of space. So this type of perturbation is only going to be applied to things that are less than 100 megaparsecs or so. It doesn't make much sense to apply it to anything larger or anything. In that case, we're considering a domain D here that intersects the light cone of some event x. So the full Einstein equations, which of course are the real theory of gravity, are still being integrated along past null curves. But we can make an approximation to those on this three-dimensional space M now by expanding the retarded null Green's function. In that case, we get the Green's function for the Laplacian on this three-dimensional space, plus contributions that involve time derivatives. So unlike cosmological perturbation theory, this sector of our two-parameter expansion doesn't have space and time treated on equal footing. So the expansion parameter for this sector, eta, goes like v, the velocity of matter fields in this space. And this is approximately equal to the ratio of time derivatives quantities to space derivatives of the same quantities. So time derivatives acting on things make them smaller than space derivatives do. So I'm just describing post-Newtonian gravity here, and this image is borrowed from the textbook by Eric Passon and Dick Will, which describes these things in much more detail, much more lucidly. We'll talk a bit more detail about it. But if you've got this perturbation parameter eta that describes the post-Newtonian sector, because time and space have to be treated differently in this approximation, because we're integrating off of the past light cone by expanding those retarded null Green's functions, then we have different parts of the metric expanded at different orders. So we're missing order 1 parts and order 3 parts, missing order 1 and 2 parts in the off-diagonal part of the metric here, but we do have an order 3 part in the time-space components which are absent from the other ones. So this is required for consistency when you have a system that has this kind of asymmetry between time and space. And similarly, you have different orders appearing on the right-hand side of the field equations as well. Okay. So in order to see which perturbative expansion we want to use for different systems that exist in the universe, we can consider different scales, systems that exist on different scales, so the sun, galaxy, groups of galaxies, clusters and superclusters. And these are estimates for the size of velocities, length scales, mass scales, and Newtonian potentials, which is the ratio of these two in this plot in geometric units. This was collected by Sophia Goldberg, who was one of the authors of this paper. So we have that these velocities are all remarkably similar, although they get smaller as you go to large scales, as you'd expect. And we have the Newtonian potentials that we get from these mass and length scales. And you can see that in each case, the velocity is going like the square root of the Newtonian potential. And that's exactly what we expect from the post-Newtonian gravitational sector, but not at all what we'd expect from cosmological perturbation. And there's a reason for that. On larger scales than this, we don't currently have observations that scale much larger than that at the present time, although that's likely to change in the near future. But if we look at the cosmic microwave background, then we've got temperature fluctuations, which through the Sachs-Wolf effect are related to the amplitude of the potential, which are about 10 to the minus 5 from measurements. And we've got electric polarization of the CMB, which is approximately equal to the difference in velocities of matter fields in orthogonal directions on the surface of large scattering. And from observations, this is about 10 to the minus 6. So these two things show us that the velocity is approximately the same size as the gravitational potential in the CMB, which means that we can't apply post-Newtonian theory, but we can apply cosmological perturbation theory. So it looks like the real universe really does have these two different sectors that behave in two very different ways. So if we take the homogeneity scale, about 100 megaparsecs or so, as a place where these two expansions meet, then we can construct a global description of both the small and large scales. And the leading order part of the field equations in this case is a mixture of the Newton-Poisson equation and the Friedmann equation. This is what we get as the leading order part of one of the Einstein's equations, which we can integrate over a region of space to get rid of the small-scale fluctuations, which are what these correspond to. And we ignore boundary terms like this, so the integrated derivative of a Newtonian gravitational field around some region of space at the scale of the homogeneity scale, then we recover the Friedmann equation. So this is the consistency condition I mentioned earlier. For the Friedmann background to exist, is that this boundary term has to vanish. That seems reasonably strict to me. So if this doesn't vanish, then presumably you have back reaction. But if you want a global background, which is the premise of this perturbative expansion, then we require that to be true. If we move on to the higher order parts of the gravitational field, which describe the cosmological perturbations, so I've just got one of these equations here, it's quite long, just to show you schematically the kind of thing that's involved. We've got a Poisson equation, or we've got a capacity acting on a cosmological perturbation, so a long wavelength part of the gravitational field. This is the analogue of first order in cosmological perturbation theory. It's the first time cosmological perturbations show up. And you can see that this equation contains a lot more terms that exist in linear cosmological perturbation theory. In fact, we've got second order gravity happening here. So we've got quadratic terms in gravitational potentials, which act like source terms for these. So on large scales, we have what you would normally think was second order terms in the gravitational sector existing in what would normally be the first order equations for cosmological perturbations. You also have mode mixing between these scalar degrees of freedom and tensor ones. So Hij here is transverse and trace-free perturbation, the spatial part of the metric, and this is on a cosmological scale, and it's coupled to derivatives of the Newtonian potential. So not only do we have quadratic terms of gravitational potentials sourcing the leading order part of the gravitational field on large scales, we also have mode mixing between the leading order parts of scalar and tensor parts of the gravitational field because of the existence of these post-Newtonian terms. So I should say that each of these quantities in this equation are gauge invariant by construction. So these are extensions of the kind of formalism that Bardeen developed, first order cosmological perturbations, extended for both post-Newtonian and cosmological perturbations at second order. So each of these is quite monstrous in itself. They hide a multitude of sins. They're constructed in such a way that they reduce to, this equation reduces to the same equation if you chose longitudinal gauge. So as well as quadratic gravitational fields appearing in the leading order part of the large scale fluctuations, we also get that the vector modes appear in order that we would expect them to for cosmological perturbation theory. So this is the leading order equation. It's a Poisson equation for the vector mode VI here, which is occurring at the first leading part is at order 3 in the post-Newtonian sector. So if we're taking the homogeneity scale as the place where these two expansions meet, this is somewhere between first order and second order perturbation theory. So this isn't what you'd expect from a cosmological expansion, but it is what's been found by Marco Bruni and his collaborators and Chris Clarkson and his collaborators when they try and work out what these things are from n-body simulations. So this does appear to be correct from those very large simulations. So this framework, I think, is potentially a simpler and more consistent way to deal with gravitational fields from nonlinear structures, especially if we're going to start thinking about testing gravitational fields on large scales. If we're going to do that with Euclid and SKA, then it looks like we have a number of terms that we wouldn't expect to see there. So in fact, there are terms in some of these equations, this one for instance, that term multiplied by the b squared, which would be order 3 in cosmological perturbation theory, if you look at something similar. Second order perturbation theory isn't going to solve this either, because in that case you're still missing terms. You include a lot of terms which are going to be negligible, it turns out. And formally, as I was saying at the beginning, you can't use second order cosmological perturbation theory to get you closer to a cosmological model that has nonlinear density contrasts, because you started off with that assumption that the density contrast is small from the outset. Okay. So these kind of terms and the nonlinear gravitational effects that are going to introduce I expect are going to be required for removing biases and searching for following on Gaussianity in next generation surveys. They provide a framework for testing gravity and cosmology for calculating relativistic effects on nonlinear structures. So what I have in mind here is something along the lines of what Camille Bombach has done using second order perturbation theory. And they also give potentially a way for interpreting the results from numerical relativity studies of cosmological spacetimes. So in particular, I'm thinking of the type of work that Julian and Alex have been doing recently on that point. So again, this is a very brief overview of something that's had a lot of work put into it by a lot of people. So these types of frameworks can be used for studying modified gravity. And the first two papers are here, the ones with Peter, as well as Ritu and Andri Nizioki. And these first two were applying this formalism to fourth order gravity, in which case you find interesting constraints on what our theories can or cannot do when it comes to the accelerating expansion of the universe. More recently, Viraj and I have been working on constructing frameworks for modified gravity, for testing modified gravity with relativistic effects in cosmology. So we've got one paper out on that already, and there's another one in preparation. We find that scalar tensor and vector tensor theories, the simplest extensions of Einstein's theory, do fit into this type of characterization quite well. Although I think Pierre's going to tell you next about large classes of theories that do not fit into this framework particularly well, I think, and where we should expect quite interesting behaviour. We're extending these papers that I've been telling you about by including lambda and extra matter fields. That's work with Sophia Goldberg and Harut Malek in preparation. And we're also in the process of working out non-Gaussianity for these relativistic terms in the field equations, which is work with Chris Clifton, which is in preparation as well. So in summary, there now exists a number of formalisms since the last of these meetings that can be used to consistently study nonlinear structures in cosmology. These result in models that feature behavior that converges towards the expectations of FRW in many appropriate limits. So you remember that curve when the number of black holes became large, approaching the Friedmann value quite elegantly as n becomes large. We also find, however, behavior that looks reminiscent of the type of back reaction envisaged by Thomas Buckup, where we have different types of, well, effectively what we could interpret as mass if it was a global Friedmann expansion. And they occur differently at different locations in space. And the integrated effect of those differences causes a type of back reaction that's similar to what Thomas proposed. We find behavior that looks reminiscent of the nonlinear gravitational wave memory found by Christodoulou. So these integrated higher order terms are relativistic, seem to me to be relativistic effects that are similar in principle to this kind of thing, which you really need either numerical relativity or a pretty good approximate framework in order to be able to study. We find a strong relationship between post-Newtonian gravity and the large scale of the cosmological expansion. So that was the integrated terms for the leading order part of the terms of expansions I showed you. But we also find mode mixing and nonlinear gravitational effects in the leading order part of the large scale perturbations. So these aren't expected from linear cosmological perturbation theory, and they can include terms that if you tried to include them in that type of expansion wouldn't appear until you went up to third order effects. Lots of terms for second order. But so far, despite all this effort, we haven't had anything that looks like dark energy. So there's no reason, I think, from these studies to think that dark energy would be an emergent phenomenon. Who knows what remains to be found. Thanks for listening.
Time for a few questions. Yeah.
Looking at your two-scale post-Newtonian and cosmological expansion, what could you summarize the effects of the cosmological perturbations on the post-Newtonian perturbations?
Yeah. So the way this works out is that the leading order part of the gravitational field doesn't have any of those perturbations in them at all, which is what you expect. I was trying to say the first few slides. In fact, if you're trying to solve the gravitational field around the Earth, you would expect to need to know the cosmology. It works out the same way here. So the cosmological ones aren't present in the leading order part, which look more like this. They only have post-Newtonian perturbations in them and post-Newtonian gravitational mass on the left-hand side there. So you solve first for those types of gravitational fields, and then they act as sources for the other ones.
So you have a hierarchy of equations.
So the different terms mixed together as you go up that hierarchy, of course.
Sorry, I've got a follow-up.
Yep.
And then, of course, you've got these conditions of no flux of the tail. So the boundary on which you integrate here, so cosmological boundary, like horizon size.
No, so it's if you imagined a setup where you had a box that had size of 100 megaparsecs, so you could describe everything inside using post-Newtonian gravity, as I was saying on the slides before, then this would be an integration over the boundary of that box. But it has to be independent of where you put the box as well, which is quite strict, it seems to be. But there it is.
So in the approach, the post-Newtonian approach with the lattice universe that you did with Viraj, so do you have a simple idea of where the back reaction term could come from, right? And especially, yeah, so this B term, especially because it's post-Newtonian, you expect it to be genuinely relativistic. So could it have a relation with the correction that you found in the exact solutions coming from the magnetic part of the planet tensor?
It's an interesting question. So this term does come from the higher order parts. If you neglect anything that's higher than any order, you wouldn't have this. This is post-Newtonian only, which is why you've got squares coming up. So it's interesting to think about that, because this does show that the B is decaying, in fact, as you go forward in time. So that would be consistent with the effect of the kernel magnetic Wahl tensor. You're integrating back in time. So I said it increased as you go towards collapse. So it's consistent with that. We haven't studied yet how you would describe that kernel of Wahl tensor in terms of objects like this, because it's kind of, I don't hit the equations from you, but it's kind of horrendous what it looks like. So it's really a bit of a challenge. We're going to do this for a study.
Do you have any sort of limitation for what kind of derivative of the scale of perturbation comes from the gravitational wave?
Could you repeat the question so that we could hear it?
Do you have a physical interpretation for what that kind of term corresponds to?
So it's an interaction between gravitational waves and post-Newtonian gravitational potentials. So you'd expect a term like that to show up the second order in cosmological perturbation theory, although every term in this equation is the size of a first order term in cosmological perturbation theory. It's kind of the novelty of the way it occurs here. This is what you'd expect to be a high order term. So it's the interaction of those two types of gravitational fields which decouple at linear order, that decoupling the theorem is at higher orders than linear. So it's kind of a generic interaction when you have nonlinear gravity.
Any other questions?
Just a question. So, as of what is the earliest period of time where you can start this procedure?
So that was why we were including radiation as well, so we could try and extend this further back, I suppose. I think there will be a limit to where it makes sense to describe matter fields using post-Newtonian perturbation theory, I think. I'm not sure exactly where that would be. I kind of got in mind the later stage of the universe where things like galaxies exist. If you go back to recombination or anything, I think this would be a very murky way to try and interpret physics. I wouldn't recommend it. I think too much extrapolation.
Would it make any sense to promote that L, that homogeneous length scale, as a sort of a physical observable test for kind of behavior?
Yeah, I think so. So the L here corresponds to the side of the boxes here. So what we had in mind when we were doing this is that the boxes would probably be something like homogeneity scale, I suppose, pretty much more of the real universe. So above that scale, if you did some kind of smoothing, if you integrated with some kind of smoothing function, then you would end up with something that's very close to homogeneous. So I imagine this as being something like 100 megaparsecs.
So how feasible is like physically testing this kind of behavior?
So these terms would be very smooth in the late universe. So it's in principle possible, but I don't think it's going to be very big. It's a practical test.
When does it become any relevant, if at all?
It grows when you go back in time.
Okay, which is progression.
So this term goes like 1 over 8 to the 4. So when you get close to when you get to radiation relation, this is the same size as this. As I said, you don't want to extrapolate quite that far.
So around equality.
At equality, this would be the same size as everything else. So it'd be order 1 if you probably like this, which I don't recommend. But there'll be some interpolation to be very tight. And we'll go back.
Okay, let's thank the speaker again.